All right, so let's actually practice going back and forth between polar and Cartesian coordinates and vice versa. So we're going to practice converting points from one coordinate system to the other coordinate system. So in this first example, let's convert this point in r and theta. So again, we're starting off in this with a polar coordinate or a point defined in polar coordinates to something in Cartesian coordinates. And the way in which we approach these types of problems is by starting off with remembering our translation equations, or how we can take those right triangle ideas and basically go back and forth between different coordinate systems. So for us, we used all of those right triangles to derive basically 4 equations that we can use to help us go back and forth. So it looks like since we are starting with a term in polar coordinates, that we're actually going to use kind of these ones on the right or left side. And the way in which we know that is we want to go polar to Cartesian, so we want equations that are x and y equal something. So for example, in this case, we can start off by saying, well, in terms of our polar coordinate that we're given, we're starting off with r equals 5 and theta equals 2 pi over 3. And before I start jumping in right away to all of these just translation equations, I also just like plotting out the point so I know exactly where this point is. So just on this coordinate plane here, we know that polar coordinates, they still live on the xy plane. And in this case, r is equal to 5. So we're a distance 5 away from the origin at an angle of 2 pi over 3. So an angle of 2 pi over 3 will take us from the first quadrant all the way into the second quadrant. So that's our angle, 2 pi over 3. And basically from this angle, what I want to do is start at the origin and then just move out a distance of 5. Okay, so in this case, r is equal to 5 and our theta is equal to 2 pi over 3. So I know exactly where this point is that I'm trying to describe in Cartesian coordinates now. We need a negative x value and a positive y value since we're in quadrant 2. All right, so let's start using our translation equations. We have x is equal to r cosine of theta. So we can just plug in what we know. R is equal to 5. And theta here is equal to 2 pi over 3. So that is our point, or the x value. We can do a similar thing for y. Y is equal to r sine theta. So we're just plugging in what we know. We know r is 5 and theta is 2 pi over 3. So that's our point. We need to make sure that we're actually landing at the correct point though. So let's take this one little step further and remember what we know about the cosine and sine of certain angles. Well, in this case, 5 is equal to 5. Cosine of 2 pi over 3 is equal to a negative 1/2. And sine of 2 pi over 3 is equal to square root of 3 over 2. So our x and y values are actually, x is minus 5/2 and y is 5 square root of 3 all over 2. So our new point in x and y coordinates or Cartesian coordinates is equal to minus 5/2 and 5 square root of 3 all over 2. And that would be our final answer in this case, converting that point from polar back to Cartesian coordinates. And this point is landing us in quadrant 2, which is what we expect. Quadrant 2 has a negative x value, but a positive y value. So that's why I like plotting these as well to make sure that our final answer does make sense. So let's practice another example. We'll convert r theta equals negative 2 pi over 4 to Cartesian coordinates. So again, we're starting off with something in polar coordinates, and we're trying to take it over to Cartesian coordinates now. And what I'd like to do in this case is, even though we're going to use those same translation equations, I'm still going to plot this point. And there's a couple reasons why I want to try and plot this point. The first thing is we need to go up an angle of pi over 4. So again, we're starting from the x-axis. We're still on the xy plane after all. I move up an angle of pi over 4. But what's a little funky about this particular example is we have this minus r value. So what does a minus r value mean? Because again, we're thinking of r as a distance from the origin. And we haven't talked about this until this point. A negative r value would suggest, well, a positive r value, I would march up on that line a distance of 2. But since we have a negative r value, I'm actually going to reflect over the origin that distance at that same exact angle though. So where that actually takes us after reflecting over the origin is over into the third quadrant. So this is actually the point r theta equals -2 pi over 4. Again, we're basically at that same angle. It's just because of that negative r value that we reflect over the origin and we end up now in quadrant 3. So let's recall our Cartesian coordinates, how we go back and forth. So we have x is equal to r cosine theta, and y is equal to r sine theta from our translation equations a few moments ago. So let's plug in what we know. We know r in this case is equal to, well, -2. So we can plug in -2 everywhere there's an r. And in this case, we know that theta is, well, pi over 4. All right, so let's just quickly go through those angles. Cosine of pi over 4 is square root of 2 over 2, or 1 over the square root of 2. And sine of pi over 4 is the same thing, square root of 2 over 2, or 1 over the square root of 2. So we have -2 times 1 over the square root of 2, which we could reduce this at the end of the day to a minus square root of 2 and a minus square root of 2. So our new xy coordinate turns out to be minus square root of 2 and minus square root of 2. And now, since both x and y values are negative, this does suggest quadrant 3. Which makes sense because up above, that is exactly where this point landed in the xy plane. It landed itself in quadrant 3 because a negative r value reflects us over the origin and puts us over into the other opposite quadrant. Okay, so let's do another example, but this time take a point in Cartesian coordinates and convert it over into polar coordinates. And again, the first thing I like doing for this is just plotting these points out. So we're plotting points always on the xy plane. In this case, we're starting off with a point in Cartesian coordinates, so rectangular coordinates. So we move over 1 in the negative x direction, and we move up 1 in the positive y direction. To land us this point in quadrant 2, xy is -1, 1. So let's remember our translation equations to help us take this point in Cartesian coordinates and move over into polar coordinates. So we have these two sets of translation equations. We're looking for the Cartesian to polar. Another way to say this is we're starting off with a point in xy coordinates. So we need equations that say r is equal to something, theta is equal to something, and those are those equations on the right-hand side. So let's actually just go ahead and get rid of those equations on the left side, since we don't need them in this example. So I'll just move these equations over for us. And we can start plugging in values that we know. So let's start off with the polar radius, finding values of r. We have r squared is equal to x squared plus y squared. So plugging in what we know for x and y, we have x is -1, y is 1. So just plugging in what we have that r squared then is equal to 2. So we can solve for what r should be, or the polar radius from this, by taking the square root of both sides. But now if we take the square root of both sides, we get a plus or minus sign attached to that square root. So next, let's start off with, or let's figure out what that angle should be off the x-axis. So our other equation we can start with is theta is equal to the arctangent of y over x, which in this case means the arctangent of y over, or sorry, of 1 over -1. So we just get an arctangent of -1. The arctangent is between -pi/2 and pi/2. So this is actually kicking us an angle back of -pi/4. So remember, an angle of -pi/4, if we just drew this, would end up in quadrant 4. But we can know that this is actually going to be the same type of angle if we reflect, or it gives us the same line if we reflect that over the origin. So we're given this angle of pi/4 or -pi/4, but that's just because our tangent is between -pi/2 and pi/2. In terms of sort of that line through the origin, this is also the same angle for us as 3pi/4. And the reason I'm bringing that up is a hint is basically because for our polar radius, we were given both plus and minus that square root of 2. So now we have a chance to combine these plus and minuses with the appropriate angle. So we have actually two different polar representations of this point in Cartesian coordinates. So the first one, if we take just as, let's take the positive value of r, so that would be the square root of 2. And again, I'm emphasizing the positive square root of 2. What that would mean is I need an angle that would just put us into quadrant 2. Again, because if I have a positive polar radius, that's saying, again, I'm just moving in that direction. So I need an angle that will put us directly in quadrant 2, which in this case means that that angle would have to be 3pi/4. Now, on the other hand, we could also choose the point with the negative polar radius. So negative square root of 2. And what that means is we would need the other angle there, the -pi/4. So let's just make sure that that makes sense. So again, we're on the XY plane. So let me just write that in the previous one as well. If my angle is -pi/4, that lands us in quadrant 4. But because that r value is negative, rather than move out a square root of 2 distance in that direction, I'm going to reflect over the origin and move a distance of 2 in the opposite direction. So both of these points represent the same Cartesian point. It's just that one has a negative polar radius and the other one does not. So we get to choose the angles that correspond to that particular value of the polar radius, the positive one or the negative one.